Now looking at our design example 2, which if you remember was our flat plate design. Again, for bending, we can put in the numbers into our calculated bending moment diagrams, and from there we can get our hogging design moment at the end span, and we can get our design sagging moment at the end span, because as we can see, the critical is always the end span and not really the internal ones. So once we have that calculated, now it's time to plug in into our equation again. So this time we're actually going to start with N16 at 300 as a minimum reinforcement, because we are looking at a thicker slab, and that is about that is slightly more than 0.2% reinforcement. And again, same calculations, we are going to go with 30 cover because again this is a flat slab, and as we're going to see later on, typically the axis distance required for a flat slab is actually thicker than a one-way slab. So I've started with a thicker cover just to account for that based on previous experience. And you deduct in the bar size now because, well, this D now is because we have reinforcement in two directions. The first direction is going to be the cover minus 16 on 2, and the second one is going to be the cover minus 16 on 2. So if you take the average of these two, you end up with just the center line between the two bars, which is the total depth minus the cover minus 16, and that is just, I'm taking it as an average in two directions, so I don't need to repeat the calculation with different effective depth values. Just that speeds up the calculation. It's not going to make a big difference as long as we have a good margin over the required design value. Our width, we're taking it as a 1 meter because our design moment, again, we spread it over the width of our column strip here, if you remember. And we're going to go with a 40 MPa concrete grade instead of the 32 because flat slabs usually work hard in punching shear. So it's always a good to start with a 40 MPa. And if we see that we can reduce it, it's not going to make much difference from bending, as the concrete grade is generally governed by shear capacity in this case. Now, if you put all of this value into our equation, we get about 70.9, which is clearly and expectedly nowhere close to what is required for a column strip in a flat plate. It's only 70.9. So let's try to add some additional bars. Say if we try to add N20 at 300s, that only gets up to 175, still not enough for the hogging moment. How about we add N24s at 300s? That gets up to 219. Let's check. Yep, that covers the 200. So N24 at 300 additionals and the original N16 at 300s everywhere is gonna do it over here. Also, one important thing, we are designing our column strip for all of the forces, but the code still requires a minimum sagging reinforcement to be designed in the middle strip, and the minimum for that is pretty much 30%. So I'm just gonna check my middle strip for this 30% of the sagging moment. So my sagging moment was 164. If I take 30% of this sagging moment into my middle strip, that is about 50 kilonewton meter. And with the minimum N16s I have there, that gets me more than enough for what is required in my middle strip. So with that in mind, if I'm really going to detail my slab reinforcement as practical as possible and as efficient as possible in this case, I'm gonna put my N16 at 300 bars everywhere, because as we are going to see, that is the minimum as a starting point, and then we are going to add our N24 at 300s top and bottom only in the column strip. And as you can see here, I indicated that this only applies for a width of about 4.2 meters. Now that is quite efficient, not as efficient as possible, because if I go back and I look at my bending moment, I only need the N24's additional here and here at the top of the column strip. Down here, I probably can do with much less moment, so I can probably do with only, let's say, N20 at 300s additional, and over here at the bottom, I also know that N20 at 300 additional is going to be enough. Only at the top here is where I need the N24s at 300 additional. But changing the additional bars a lot, especially the size between N24 and N20, it can easily get confused which one goes on top, which one goes on bottom. So my personal preference here is to keep the additional the same, and just add it in the bottom as well as I'm adding it in the top. And the difference is actually quite little here. It's not that much. And obviously over here I've marked the reinforcement only in the X direction because that is the strip we are designing. But this reinforcement is pretty much going to apply in the other direction as well, pretty much because we have the same spans and the same loads and we're designing in the two directions. And if we do some calculations over here, we can see that this results in about 28.4 tons of reinforcement, excluding the laps and cogs. Now, this is sort of balanced between full efficiency of just putting the bars required at the locations required and full inefficiency but simplicity of putting blanket reinforcement, which is the same reinforcement everywhere in the flat plate. If I put the same reinforcement everywhere, I'm just gonna have to go with the worst case, which was the N24s, and I'm gonna have to put that everywhere. And that pretty much results in the reinforcement being 45 tons instead of my 28, and that is about 60% extra reinforcement in the floor. It is very simple. As you can see on the plan, I just have one reinforcement everywhere in the slab. That is very easy to get right. You would hope so, at least. But it results in 60% extra reinforcement. Now that might be acceptable if it's only one floor or if it's only two floors, where 60% extra reinforcement is not the end of the world. But if this is, for example, 15-story, 20-story, 30-story building, or even higher than that, if it's 60, 70, 80, 100-story, this difference adds up quite easily. Once you are more than 4 to 5 stories, the significance of making an efficient floor design becomes more and more and more important. And that's when comes a third solution in the picture. We can actually go with a blanket of N20 at 200s, even though it doesn't work for strength as it is. But what we can do is we can reduce our end span to 7 meters, and we can increase our internal spans to 9.5 meters. This way we maintain the same size of the plan, but because we have a shorter end span and we have a longer internal span, the moments balance out now. So I don't need to put additionals at the end span, and what was required for the internal span is required everywhere now. So I can go with just my N20 at 200 everywhere, and this is gonna give me about 31.3 ton, which is only about 12% extra compared to the original proposal. So I achieved my simplicity in design, and I achieved very efficient design still. It's not the most efficient, but it's as practical as possible. Sometimes that is part of being efficient, so there's less chance of errors being happening on site. And generally 5 to 15% within the absolute minimum is acceptable in practice. But to achieve that, I have to change the concept. I have to position my columns in a more efficient way. Now, in a smaller building where it's only 1 or 2 floors, most of the time as an engineer you don't have the freedom to move the columns a lot because the architectural design is actually more important. But if this is a tall building, 10-story, 20-story, 30-story, you have a bigger input in the project, because where you put the columns affects the structural efficiency, affects the base of the building quite considerably, and then understanding the principles of moments and deflections, and detailing the reinforcement and sort of the like, and balancing the floor slabs in the building results in a more efficient building that's still quite simple. So if it's up to me, I will go with this option if it's only 2-story, and I will go with this option if it's a high-rise building that's quite repetitive number of floors. But I will never go with this one that is about 60% extra, because that is just, in my opinion, waste of reinforcement. And we shouldn't be designing floors for construction that has more than 30 to 40% extra reinforcement than what is required, just to maintain our sustainability goals as professional engineers and our responsibility towards the environment as well, because this additional reinforcement is not really easy to produce and it's not sustainable, so you have to be very mindful of the resources we are using in construction. This video is part of Concrete Floors Design course that's available online on Udemy. If you'd like to watch the full course, you can access it via the discounted link from the description of the video. When you click on it, you'll be able to purchase the course for a heavily discounted price than the original price, and you'll get access to about 4 hours of lectures on floor design covering all areas from analysis to flexural, including bending and shear, as well as deflections and vibrations, minimum requirements, durability, and fire design.